Okay, so another bond theory is valence bond theory, where we discuss hybridized orbitals. Because it's found that the orbitals that we do have that are on the central atom often aren't in they don't have the right shape or the right orientation to be involved in the bonding that we see by experiment. So for beryllium, we know that we have two bonds, and they're 180 degrees from each other. But beryllium, if we write out its orbital diagram, and what we're going to do is only draw the, let me put it over here. For beryllium, we have, well, since it's small, I'll do the 1s, and then we have 2s. Couple of things. We know that for bonding we need two half-filled orbitals. We have none here. We also have just 2s orbitals. We don't have ones which are just spherical, so it doesn't seem like that would work. So what we end up doing, Linus Pauling was the one who came up with this idea, showed that if we elevate an electron from the 2s into one of the empty 2p orbitals, now we have two half-filled orbitals. These are core electrons, and we won't normally draw, I won't draw these again. These aren't involved in bonding. These ones are, though. And what happens is remember, the orbitals are just the place where the electrons go. So if we bring in the electrons from other atoms as they start to bond, these guys will shift and mix and hybridize into what we call sp orbitals, because it's one of the s's and one of the p's, so sp. And we have two half-filled orbitals now. Because they've hybridized and changed around, they end up looking, all of these hybridized orbitals we'll look at have the same basic look to it. They have this larger lobe and then a smaller one. This one is involved in bonding. This is just kind of extra. It just happens to be there, but we don't normally worry about it. It looks kind of like a balloon. And what we normally do is we leave off that little part that isn't really involved in bonding very much and just draw it as in this form. So that's what I'll do here. So this asks us to draw this, so you put in and label. We have sp and sp. Each of these has an electron. That's what we have here. And then the fluorines come in, and the fluorines come in with their two p orbitals, half-filled. So these are two p's, because fluorine is, for fluorine we'd have it's 2s, and then it has one, though I drew it very teeny tiny. Let me redo this. So 2s, 2p. So it has one p orbital that is half filled, so that one would be ready for bonding. And you might say, well, then what does the fluorine do as far as hybridizing? It doesn't have to hybridize because it only bonds once. It comes in and can just click in any orientation. It's the beryllium that needs to bond to two at a time. So it has to adjust. So the inside or the central atom always hybridizes. Always, always, always. Even if it appears that you don't need to do any hybridizing because everything is set, still you have to hybridize. The outer ones never do. They never hybridize, so keep that in mind. So for boron, let's write out the orbital diagram. This is what you may asked to do. Write it out only for the valence electrons. So we have this. Boron is 1s2, 2s2, 2p1. And just make sure that, yeah. And we don't have to draw the core electrons. We know that boron, might as well write out the Lewis structure, so you can see that the stuff that we learned the last chapter just keeps coming up over and over. And then we have this electron is elevated to this position into this half-filled orbital over here. So now we have three half-filled orbitals, so we have enough orbitals for bonding, and they're going to hybridize. They're going to change their shape. They're all now sp2s. So we label each of them as sp2s, not as two sp2s. We don't do that. We don't put a number in front. We just put sp2. Now that s indicates we have one s orbital, and then the p2, the 2 indicates we have two p's that we've used. So it's sp, now we're sp2. Now we draw it like this. We draw each of them and label them as sp2s. And once it gets too messy, we can use arrows to indicate them. We can just draw sp2 once and then draw arrows to it. We have the fluorines above here. There. And the fluorines are 2p's. And I don't know if I wanted to draw the bonds with the following. And that's as far as you go. You can always put in like the 120 degrees, that kind of thing. But that's it. So you need to show the elevation of the electrons, the promotion of electrons, the hybridization, and then show the bonding scheme. For methane, we have carbon, which is 1s2, 2s2, 2p. And you're only going to want to draw the valence electrons because when we get to the higher, the atoms with more electrons, this might be 4s and 4p. Do you really want to draw the whole, be all the other dozens and dozens of electrons? We don't want to do that. So we just accept that the core electrons are not involved in the bonding. Here is carbon as is in its ground state. We know that we have to form 4 bonds. That's why we draw the Lewis structure, just so we can see how many bonds so we see we have 4 bonds. We're going to need 4 half-filled orbitals. So if we promote this electron, it goes here, and then we hybridize. And we create 4 half-filled orbitals, and they're each labeled as sp3. After a while, it's better to just put sp, the hybrid orbital name, and just put ... and that's fine. But you got to know that, what you should know here is that they're all the same. They all have the same label to them. And then, because of the way they've been hybridized, they all go off at 109.5 degrees from each other. Oops. So each of the carbon, the sp3 orbitals, will then be bonding with the hydrogen, which is a 1s orbital, brings in one electron. So I'll require that you draw the names of those orbitals of the things coming in. So you need to know, mostly it'll be fluorine and hydrogen, but it can be chlorine too. And chlorine will come in with its 3p orbital, rather than the 2p orbital like the fluorine. So just be careful. The ammonia, well, nitrogen is 2s, 2p. Now, the reason I had said, made the big point of the central atom being hybridized is that this is already set. You don't have to promote any electrons. It has 2, it has a lone pair, and it has 3 electrons that are orbitals that are half filled. So these are ready for bonding, but they're not in the proper orientation, so you have to hybridize them all. So these are sp3s. So the nitrogen, the 1 sp3 contains a lone pair. Then the other 3 are half-filled and ready for bonding. So you can draw arrows to them if you like. Try to be as neat as possible so I can read what you're doing. Even as fast as I'm moving, this is still, you can see everything that you need to see. You can see the bonds, the orbitals, they've been labeled. You see what came in, and I've labeled those orbitals. So it might take a little work, but just make sure it's something that I can read when and there's a lot of leeway there. I've done this for a long time, so I'm pretty forgiving about the sketches, but just make sure that everything's in there and that it's not, you don't overlap everything to the point where I can't read it. Oxygen, 2s, 2p, so it's that. And again, it has, I didn't write out the Lewis structure last time for the ammonia, sorry about that, but you write out the Lewis structure, you see that you need 2 bonds, so 2 half-filled orbitals, and then 2 fully filled orbitals for the lone pair. Here's your 2 fully filled orbitals. Here's 2 half-filled orbitals, so they're all set to go now. You just have to hybridize them into the sp3s. Then oxygen, you'll have 2 lone pairs. You'll have 2 half-filled orbitals. These are all sp3s. There, 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 and there. And then you have the hydrogens that come in with their 1s. And labeling those orbitals that are coming in will be very important. So phosphorus. Now we get to see, I should point that out. We knew that beryllium is exception to the octet rule. Now we see why, because it was able to form, all it's really able to form with its valence electrons are 2 half-filled orbitals. It doesn't have the ability to form 4. You can say, well, we could take those core electrons, promote that, and then we'd have 4 half-filled orbitals, but that'd be really tough to do. Same with boron. It can only form 3 half-filled orbitals. There isn't a 4th half-filled orbital for that. Now for phosphorus, we know when we draw out the Lewis structure that we'll have 5 bonds, no lone pairs, so we need 5 half-filled orbitals from phosphorus. Alright, so phosphorus is in the next level down, next row down, so it's that. I'll make sure, I don't think it's in. Yeah. And now now that we're in the 3rd row, we also have access to the 3d orbitals. They're empty for phosphorus right now, but we have access to them. There's no 2d orbitals, so we can't do this with nitrogen, which is in the same group. So we have this. And we know that we need to form 5 bonds. Why? Because nature says so. We know that this molecule exists, so we have to go with what we've seen in nature. We know that it forms 5 bonds. We know we've never seen this. That doesn't exist. And we know why, because there's no 2d orbitals. So if we're going to create 5 bonds, we need 5 half-filled orbitals. So if we promote this electron up to here, now we have 1, 2, 3, 4, 5. So these are all hybridized. Nitrogen can't do that because there's no 2d, so that's why it only forms 3 bonds. But phosphorus has access because it's a larger molecule, it has more electrons, more levels, and more sublevels to work with. These are called these are all sp3ds. And you can just write it like that, indicate that these are all the same, but you have to label them. Then phosphorus, okay, now we got a little work to do. These are going to be trigonal bipyramidal. Got a lone pair, or got one single electron in each of these orbitals, So these are all sp3ds. So you can put arrows, and it will look a little cluttered, but just make sure that I know which ones are which. Do it that way, or you can label each of them if that suits you better. And then the fluorine comes in with its 2p. That dumbbell-shaped one, so it's not coming in with 2 orbitals, it's coming in with one that has 2 lobes to it. The sp3d also have 2 lobes. Remember, the second lobe is very small, and if we were to draw it, as cluttered as this looks, the sp3s, we're drawing them like this, but they really have a lobe on the end. Well, we could put that in, but we'd have to do this. It'd be kind of messy, so we like to leave that off, but that's the structure. If you want to show the geometry a little bit better, you can connect things. Might make it matters even worse, but there we go. Then we have sulfur tetrafluoride. So we write out the structure. We see we have 5 pairs of electrons around the central atom. One is a lone pair. And we know that I have here SF6, so it can do either. So let's see how that's possible. So sulfur is in, it's in the 3rd row, I believe. Make sure, I know it is, but I just want to double check. That 1% chance that it's not. Hate to label it incorrectly. Now we need 5 orbitals. Here's 4, so that means we're going to have to go into the D's. So we start out like this. We need 1 lone pair. Looks like we have it there. If we promote this guy up here, then we have 4 half-filled orbitals. So we have exactly what we need. 1 orbital for the lone pair, 4 for the bonding. We hybridize these. Now I haven't mentioned this before, so this is sp3d. Lone pair, ready for bonding, and then sometimes they'll just bring these down to show that they didn't disappear. They're just not filled, we're not using them. And that's fine, either way you want to do that. If you want to just show that these last orbitals were not part of the hybridization, that's fine by me. I'll be looking for that though. So the sulfur, we have 1, 2, 3, 4, 5. The lone pair goes equatorial, and then we have this, and then we have the fluorines. I'm going to label everything at the end. Fluorines is what gives you the trouble, but we can't use hydrogen for everything, which would be nice because then it's just a nice little circle. But this is sp3d for each of these, 2p for each of these fluorines, 2p, and there you go. Just gotta kind of scroll up so you can see everything at once. Now sulfur hexafluoride, draw that out, see what we're looking for here. Looks like we have at least 6 bonds, and 6 bonds is or 6 electron pairs is as far as we go. So 6 bonds is, when we see this, we know that's all we're going to have. We aren't going to have any lone pairs because we're not going to have 7 or 8. It goes up to 6. We're using all 6 for bonding. So the sulfur, write it out again. So it looks, it's going to be the same element. So put this here. 3s, 3p. This one gets promoted. Now we have 4 half-filled orbitals, not enough, so we promote another one. Now we have all 6. So now we get to the highest number of hybridized orbitals, which is 6, and this is going to be sp3d2. S for 1s. P3 means 3 p orbitals were used, not this 3, but 3 total. And then we have 2 d orbitals that were used, so d2. Like so. Now I'll try to draw this a little smaller, though that's going to be tough because it's the largest one that we've come across so far. And then F, and we use fluorine, as I said a few lectures ago. We use it because it only bonds once. And a lot of these other compounds with the other halogens don't exist. They'd be too unstable. Fluorine is very stable, or forms a lot of stable compounds. And these are 2p's, so you label them each. I know it's a pain, but I'll make sure that you know that these are all 2p's. And then the 6 here are sp3d2s. So this one, and this one, this one, this one, probably. It's easier just put the last 2 like that, and you've labeled them all. Okay, now we got 17 minutes, 6 more to go, so we'll go to the next video.